Hello there, and thanks very much for tuning in to this South by panel titled Wildlife Rangers Armed with Artificial Intelligence, or AI. My name is Erwin Ganshanani, and I serve as the Deputy for the Computer and Information Science and Engineering Directorate at the National Science Foundation in Alexandria, Virginia. I'm also wearing a second hat at the moment as the Senior Advisor for Translation, Innovation, and Partnerships in the Office of the Director. Now, as many of you know, the National Science Foundation, really since our establishment in 1950, has sought to promote the progress of science to advance the national health, prosperity, and welfare, and to secure the national defense. And we've done this by supporting fundamental research in nearly all fields of science and engineering, everything from astronomy to zoology. And we do so largely in the form of research grants or cooperative agreements to universities and nonprofits, and sometimes to small businesses as well, to be able to largely support faculty and students in conducting research. Now, we brought today's conversation specifically about wildlife rangers who are now armed with predictive artificial intelligence. We brought this to South by because we wanted to have an opportunity to talk about how federal investment in AI is really transforming society, and specifically how it can have tremendous impact when it comes to conservation and sustainability as well. Now, I'm going to give you one very specific example in this context of conservation and sustainability, and it's going to be the focus of our panel today, and that is animal poaching. Now, some of you may have heard about this. Poaching is the illegal hunting, capturing, or killing of wild animals. And unfortunately, it's common in some parts of our world, and it's done for a number of reasons. For example, some folks poach because they want to be able to claim the land that the animals reside on for human use. In other cases, folks poach because they want to be able to retrieve and use rare animal products, things like ivory or fur, even organs, skin, and bones. And they often do this because they feel that these products can have religious, medicinal, nutritional, financial value, even if that may or may not be the case. In fact, some animal populations today around the world are endangered specifically because of this poaching that takes place. And unfortunately, the problem gets even worse too. It's not just that the poachers go after the animals, but they are often so motivated that they will actually end up harming or even killing wildlife rangers to elude the detection or capture of their poaching. And so what we have before you today is a tool that attempts to combat this problem. It's called Protection Assistant for Wildlife Security, PAWS or PAWS. PAWS is essentially a predictive AI software that can crunch massive amounts of data and leverage machine learning to be able to suggest the most effective patrol routes for wildlife rangers. And this effort, this tool, this effort, it's really the result of our distinguished panelists that we have here with us today. Now, I'll introduce them in just a moment, but before I do, I want to give you a couple of things that I'd encourage you to think about and listen for as we have this conversation today. I hope you will be able to see the value of fundamental research in tackling real-world problems, and how NSF scientists, scientists in the community, and others are working together to be able to enable positive societal impact in the context of those real-world problems. I also hope that you will see a tremendous amount of synergy that exists between what we call foundational research. So another way of thinking about that is curiosity-driven or exploratory research, and more translational research. Research that's much more use-inspired, much more solution-oriented in terms of what the end goals are. This is really, in our view, a very iterative process. And finally, I hope you'll take away that when we do talk about use-inspired research, solution-oriented research, we're often talking about bringing the domain experts, wildlife rangers, for example, together with researchers, AI scientists, to be able to understand the problems that the domain experts are facing, and to be able to have them help us really co-design the solutions that we'd like to be able to see. That co-design, that teamwork, that collaboration, That is an important value that I hope you will take away from this panel today as well. So with that, let me start by introducing my colleagues, folks I'm pleased to call colleagues who are serving on this panel with me. First, we have Milind Tambe. Milind is the Gordon McKay Professor of Computer Science and the Director of the Center for Research in Computation and Society, CRCS, at Harvard University. He also, by the way, wears a second hat. He serves as the Director for Social Good at Google Research in India. Milind is a fellow of the Association for the Advancement of Artificial Intelligence, as well as a fellow for the Association for Computing Machinery. And he has received a number of awards throughout his career for his many research and education accomplishments. Next, we have Shirzad Gawami. Shirzad is a data and applied scientist in the AI for Good research lab at Microsoft. Her research is specifically centered around the development of machine learning models and artificial intelligence algorithms to be able to solve grand societal and environmental challenges at scale. We often refer to these as AI for good or AI for social impact. Before joining Microsoft, she completed her PhD degree focused specifically in this area at the University of Southern California and working very closely with Milind as well. Third, we have Bistra Dilkina. Bistra is an associate professor of computer science at the University of Southern California. She is also the co-director of the USC Center for AI in Society, CASE. And I think most importantly for her, she is one of the early career faculty leaders in this young field of computational sustainability. She has co-organized workshops, tutorials, special tracks at major conferences over the last several years, specifically on computational sustainability and related sub-areas. And her work really spans discrete optimization, network design, stochastic optimization, as well as machine learning. And then finally, last but certainly not least, we have Lily Zhu. Lily is a PhD student currently studying computer science at Harvard University in Milind's group. She's being advised by Milind. Lily seeks to apply research in AI, specifically in online learning and game theory, to the broad challenges of sustainability. And she's passionate about reducing her own negative impact on the environment and increasing her own positive impact on society. And I think you'll see that through the course of her presentation and this panel discussion. So the way we're going to do this is we're going to have each of our panelists talk a bit about their work, their engagement on PAWS. We've asked each of them to spend about 5 or 7 minutes doing that at the outset, and hopefully that will save us about 10 or 15 minutes at the end for Q&A and a little bit more of a discussion as well. So with that, I am pleased to cede the floor, and I'm going to turn things over to Milind to start us off and say a few words, broad brushstrokes about PAWS and what this project is trying to achieve.
Hello, my name is Milind Tambe, and I'll be talking about wildlife rangers armed with AI. So this is a presentation where I'll give an overview of our PAWS work, and then my co-panelists will discuss some of the details, dig into some of those details. In wildlife conservation areas around the globe, such as this Queen Elizabeth National Park in Uganda, there's wonderful wildlife, elephants, giraffe, and others who are endangered wildlife. But there's threats to this wildlife, traps, snares that are placed by the thousands by the poachers to maim and kill this wildlife. So consider this Queen Elizabeth National Park with 2,000 or more square kilometer area and just 100 or so rangers who are trying to find these snares. It's extremely difficult. So can we arm rangers with AI to help them? And that goal was the birth of PAWS, Protection Assistant for Wildlife Security. It's an AI system based on machine learning and game theory. The machine learning portion comes in to make predictions of where are the poaching hotspots. And the game theory portion helps prescribe where the rangers should patrol, anticipating poacher reactions to our patrolling strategies. To build PAWS, we can imagine going back again to the Queen Elizabeth National Park. We can divide this park into 1 kilometer by 1 kilometer grid square. So there are thousands and thousands of these grid squares given the large area of the Queen Elizabeth National Park. And the goal for PAWS is to then predict which of these grid squares have a high probability of finding snares, the high risk areas, and then to give patrol recommendations to our rangers. To build PAWS, we got 10 years of poaching data from Uganda. This data includes, for each grid square kilometer, range of patrol frequency, animal density, distance to rivers, roads and villages, area slope, area habitat, and many other features. And then we are trying to predict, based on this data, the probability with which we will find snares per 1 kilometer grid square. So we built the system, we tested it in the lab. In the lab, it was working great. But working in the lab is just not sufficient for our collaborators, Wildlife Conservation Society, Uganda Wildlife Authority, and others. They wanted to see an actual test in the field. So the first ever field test for PAWS was in the Queen Elizabeth National Park in 2016. We selected 2 9 square kilometer areas that were infrequently patrolled. Those are shown with these green dots. The red dots are where poachers had placed traps or snares in the past. We are asking rangers now to go to completely new areas they haven't patrolled for many months or even years, and predicting that they're going to find snares there. And the point here was to not go back to places where they found snares, but to go to newer areas to show the power of machine learning being useful to make predictions in newer areas. So we sent these predictions over, and now the question is, the rangers were going to patrol this for a month. Are we going to find snares or not? This is a big test for PAWS. And rangers started patrolling, and we were waiting in our lab for results. And every day the rangers would send back an email as to what had happened that day. And initially there was nothing. And it started getting a little bit difficult for us, waiting for what might happen. But then came news that they actually had found a poached elephant with its tusks cut off, a very unfortunate event. We were too late to save this elephant, but at least the machine learning system had pointed them in the right direction. Soon after, a whole elephant snare roll was found and removed. So poachers were active in the area. They were killing elephants in the area. But before they could kill the next set of elephants, a whole elephant snare roll was found and removed, thus potentially saving lives of elephants. Then a whole set of antelope snares was found and removed. So PAWS was clearly successful in this pilot test. Now it was time to do a larger scale test. And here, the test was done in 3 separate national parks: Queen Elizabeth, Murchison Falls, and Srepok Wildlife Sanctuary. We selected areas which were infrequently patrolled, because remember, we are trying to get rangers to go to areas they haven't patrolled before, because that's what we are trying to make predictions about. Now we selected some of these areas, made predictions that these areas are going to be high risk, and other areas PAWS predicted were low risk. Having made predictions about high risk and low risk areas, rangers were then asked to patrol these areas. They weren't told, of course, which are high risk and which are low risk. For 6 months, the rangers patrolled in each of these parks, and then they came back with results. And what we found is, where PAWS made predictions of high risk, indeed more snares were found. Where PAWS made predictions of low risk, less number of snares were found. So PAWS was able to make excellent predictions in these 3 separate national parks. In fact, the number of snare captures in Cambodia from 2018, when there was no PAWS being used, to 2019, when PAWS was starting to get used, jumped 5-fold. You will hear a whole lot more about all of these tests from my co-panelists in more detail. Given the success of these tests and the success of PAWS, we are now collaborating with SMART. SMART is this partnership of 13 different wildlife conservation organizations, such as World Wildlife Fund, Wildlife Conservation Society, and many others. It's active in hundreds of national parks around the globe. PAWS is now integrated with the smart software, meaning PAWS is available to hundreds of these national parks. And in fact, testing is going on across the globe. It's a very exciting time in making PAWS available to rangers around the world in the important fight that they lead in trying to save wildlife across the globe. Now, PAWS required us to travel to many different sites around the globe, whether it's in Uganda in national parks or in Malaysia, Cambodia, Indonesia. This is important because when we are engaged in work in applying AI for society, AI for social good, we can't sit in our labs and expect the software to be developed and then helicoptered in and automatically these different non-governmental organizations to start using it. Because often the software just developed in the lab in isolation of understanding of ground situation is inapplicable to the exact constraints on the ground. Understanding these constraints on the ground is important so that we can develop software that actually fits the need. From a research perspective, this allows us to uncover completely new research challenges that would be hidden had we not visited these places. It also helps us build up trust with the user community. And so for AI for social impact, it is important to get out of the lab, to go to the actual site, to build up these interdisciplinary partnerships so that the research can flourish. A concrete example here is in Malaysia. From the lab, we could make recommendations for patrols that said go from point A to point B in a straight line. But it's only when we actually visited the area, we realized that this is a hilly terrain. And to actually make patrolling recommendations, you got to walk along ridge lines, along riverbeds. And there's a whole new problem of how to generate these kinds of patrol routes in a 3D environment using these kinds of terrain constraints using contour lines. So PAWS is an example of AI being used for social impact. It's an example of how use-inspired research comes about. Ultimately, it's trying to empower nonprofits to use AI tools directly. And our goal then is to avoid being gatekeepers to using AI technology for social impact and hand over the software so that nonprofits can start using these tools by themselves. So with this, I'm going to conclude my presentation and I'm going to hand this over to my co-panelist Shahrzad to discuss more details of some of the elements of testing of PAWS in the field. Thank you.
Thank you, Milind. Hi, everyone. My name is Shahrzad Gholami, and it's a great pleasure to be with you today. I would like to share a little bit more details about the workflow of the PAWS system and the challenges that we have been facing, and also the field tests that we have conducted in 2 national parks in Uganda. So the PAWS system is basically leveraging the data that is being collected in a platform named SMART. So SMART is a software platform that is adopted by more than 800 national parks around the world. And it allows the park rangers and conservation area managers to store, monitor, and manage the data that they have collected based on their food patrolling every day. So basically, park rangers, they conduct their patrols and they try to keep records of the animal locations, the poaching activities that they have discovered, and also the amount of the patrol coverage that they have given to each regions of the park area. So all of this information are being managed in this SMART platform. And so we are trying to use this information and we are using this information along with the environmental factor that can influence poaching activity. We transform the data and we make it ready to run some machine learning models. So machine learning models are some mathematical models that they allow us to extract knowledge and insights from these data that has been collected by park rangers. So the output of this machine learning model is basically some risk maps that gives us information about the likelihood of poaching activity across different locations in national parks. And these risk maps can be used in some decision-making models to give some fine-tuned instructions and recommendations to the park rangers about the routes that they have to take to maximize the number of snares that they find in their day-to-day job. And so this is like an iterative process, and we try to get feedback from the outcomes that we have found, and we try to improve our models over time. So in this domain, there are some challenges that exist, and they have to be addressed in the modeling. And basically, these challenges have been motivating our research, our AI research in this area. And the novel models and algorithms that we have developed have been derived by these challenges. For example, the data that the park rangers are collecting is not perfect, and there is some uncertainty with the data. So the locations that they visit, they may not find in those locations, they may not find any activities, any poaching signs, but it doesn't mean that poaching activity did not exist. It might be because the snares are well hidden, or they are placed under the in the ground, and it has been hard for the park rangers to find them. So the data is not perfect. And also in this problem, there is a temporal aspect. So this poaching activity is a dynamic process. We cannot expect the poachers to attack the same location all the time. And also there's a spatial aspect to this problem. These areas are really vast, and we have to make sure to take that into account in the modeling. And also the number of the park rangers and the security resources that are given to these areas is very limited. For example, if we look at the Queen Elizabeth National Park data, and we look at the amount of the patrol that has given to these 1 kilometer by 1 kilometer grid cells across different months, it's like the average is like 0.25 a kilometer of walk by the patrollers, which is a very a small number. Which means that having a machine learning model or predictive model can really help the park rangers to learn about the hotspots of the poachers and direct their resources to those areas to find more number of snares. So we developed the models, and we iterated over the models. We tried to improve them progressively, and we tested the models or evaluated them in the lab. But we wanted to know how these models perform in the wild. We wanted to see if these models are reliable or not to be used by the decision makers. So we conducted extensive field tests. The first field test that we conducted was in Queen Elizabeth National Park in Uganda. And so in that test, we selected 27 areas that they were 9 square kilometers each of them, and they were infrequently patrolled by the park rangers. So we basically queried our model to make predictions over these areas, and we divided them into high-risk regions and low-risk regions, and we asked the park rangers to do patrolling in those areas, and we didn't tell the park rangers about the risk level of each area to avoid any biases to be in the process. So the patrolling activities lasted for 8 months in Queen Elizabeth National Park, about 452 kilometers of patrolling by the park rangers. And then when the patrol was conducted, they sent back the data to us. And when we analyzed it, we realized that in the regions that were predicted to be high risk by our model, the park rangers were able to find more snare activities. And during this process, they actually ambushed the poachers, and they were able to collect so many snares. So we wanted to see if this model performs well across other areas as well. So we extended the experiments to another location, which was Murchison Fall Park in Uganda. In this new test, we selected 33 areas of 4 square kilometers, again, infrequently patrolled. And then we made predictions using our model for these areas. And these experiments continued for 5 months, about 440 kilometers of patrols. And the results of the experiments in this park area was also promising. And in the locations that they were predicted to be high risk by the model, park rangers were able to find more snare activities compared to the locations that they were predicted to be low risk. So because the results were encouraging and they were promising, we continued the experiments to more areas around the world, and Bisra and Lily will be able to share more details about these experiments and the scale up and operationalization of the project.
Hi, everybody. My name is Bistra Dilkina from University of Southern California, and I'm happy to be here and share with you some of the details of this project that I was involved in. I was extremely lucky to actually join the PAWS effort led by Milind in early 2018 at a very conspicuous time when they were just starting a new collaboration with WWF to try to deploy PAWS in an area, one of the conservation areas that WWF helps manage. And so this was in fact the Srepok Wildlife Sanctuary, which is located in the eastern edge of Cambodia in Southeast Asia, bordering Vietnam. And Srepok Wildlife Sanctuary is a place that is home to many species such as the Asian elephant, banteng, and langur monkeys, but is also the site of active poaching. In fact, Srepok Wildlife Sanctuary used to have a native population of tigers, but the last tiger seen in Cambodia was spotted in 2007 in Srepok, in fact, but none since then. So Srepok Wildlife Sanctuary has been identified as the best site for reintroduction of tigers in Southeast Asia. But before something ambitious like that is started, they really have to try to reduce the poaching risk in the park. And that's where PAWS comes in. In fact, Srepok Wildlife Sanctuary spans more than 1,400 square miles and only have 72 rangers on the ground. So although they have motorbikes that help them get fast from one place to another, it's a very large area to patrol and be able to detect snares that are well hidden and remove them before they're capable of killing animals. And so as with any other AI tool, it's not possible for it to work just out of the box. So when we started trying to use PAWS in Srepok Wildlife Sanctuary, a big part of this process was in fact creating a very tight feedback loop between the scientists, us in the lab, and the domain experts and local rangers from WWF and from Srepok Wildlife Sanctuaries. So in a basically, we had every 2 to 3 weeks a phone call with them where we would iterate over the data, the models we would build, the predictions, and discuss what made sense and what did not make sense. And that iterative closed loop feedback loop between us and them helped us identify some key aspects that were specific to the way that this area operates. For example, it helped us discover that in addition to just modeling distance from roads, we should actually specifically model the distance from one particular road called Route 76, which was a major through highway through the park. Other things that we identified that we initially were not aware of is that we also had to specifically model the eastern boundary of the park, because this actually coincided with an international border with Vietnam. And in fact, there were poachers that were crossing over the border into Srepok Wildlife Sanctuary, and Vietnamese poachers behave differently than local Cambodian poachers. So these are just some of the examples of the many things that this back and forth conversation allowed for. One other aspect that we had not encountered before was the fact that the dry and wet season in Cambodia are very distinctive, and the behavior of both the distribution of where the animals go and also where the poachers place their snares also changes quite by a bit between those two periods. So we actually had to build separate models for wet versus dry season. And so this, again, to make it to work effectively in the field, the key is to really treat not just AI as a magic wand, but as a decision support tool that together in a collaboration with domain expertise can provide the insights needed on the ground. And this continuous conversation with them was also critical to building that very much needed trust that both Milind and Sharzad mentioned, of the fact that this model is capturing insights about the distribution of poaching efforts, so that it can provide some additional guidance to what they already maybe are aware of. And so with this trust that we built over months and months of feedback and models, etc., we decided to move on to an actual field test, and the rangers agreed to put the effort in actually following some of the recommendations from our PAWS model in December of 2018. And so similarly to the setup that we used in Uganda, we provided them with several areas that had not been patrolled very extensively in the past, where our models predicted that there is low, medium, and high risk. And during that 1 month of on-the-ground field testing, they were actually very successful, surprisingly successful even to us. They found 5 times more snares in the 1 month that the field test was going on compared to any other month on average in 2018. And you can see here in the picture, Melinda and I on our trip to Cambodia in the spring of 2019, together with Lily, when we actually went and we were able to speak to the rangers about their experience, about following the recommendations of PAWS, about their everyday operations, about what were the challenges that they face, and what kind of AI-based inputs would be the most effective to help them guide their efforts on as they go around patrolling this vast area. And this success of this 5 times increase in effectiveness was really a spark that generated the enthusiasm to continue trying to work with PAWS and to make it something that possibly can become an everyday tool that they use, as well as start collaboration in trying to field test PAWS in many other areas. And so, in fact, I want to, before passing it on to Lily, to tell you a little bit more about this follow-on efforts in disseminating PAWS to many other areas beyond Cambodia. I want to mention and emphasize the fact that stopping poaching, illegal poaching of animals in conservation areas, is one key aspect in a larger fight, the fight against illegal wildlife trade. In fact, illegal wildlife trade is a huge, complex supply chain where the poaching and conservation areas is the source of the products, but is actually built to satisfy a global worldwide demand for these threatened and endangered species for their skins, horns, trunk, meat, etc. In fact, illegal wildlife trade has an estimated value of between 5 to 23 billion US dollars. And in fact, is the fourth in value after drug, human, and weapons trafficking. So it's a really an important problem that needs to be addressed, and yet we understand very little about it, about the structure, about how things happen, about the key players and the key routes used for this trafficking, and also have limited resources in trying to fight against it. However, the harms from illegal wildlife trade are numerous. It relates to biological invasions and zoonotic diseases. It converges with other serious crime like drug trafficking. And importantly, it undermines sustainable development investments in many of the countries where this trade happens. In fact, it's so widespread that there are more than 150 countries from which traffickers have been detected. There's more than almost 6,000 different species that have been seized. And so this is a real threat to our biodiversity. And so the idea is that AI can help not only fight poaching in the conservation areas, but in many other aspects in the fight against wildlife trafficking. And in a newly funded project by the National Science Foundation, led by my collaborator, Dr. Meredith Gore, we are trying to build the AI tools that can help with other aspects of that fight. In particular, we are building AI tools that can help infer spatially explicit supply chain networks. It can help us predict likely routes for trafficking wildlife, animals, and parts, and it can help us optimize the interdiction efforts. And we hope that with these data-driven AI-based tools, we're going to provide key decision support aids for the policymakers, for the on-the-ground decision makers to deploy the limited resources that they have in the most effective way possible. With that, I will pass it back to Lily so that she can share a little bit more about the next step for PAWS. Thank you.
Thanks so much, Bishra. And again, as everyone else said, I'm very, very happy to be here with all of you. So Bishra and Shahzad gave a great overview of all of the efforts to sort of validate our AI approach in the lab and on the ground. So the next step is to try to think about how we can expand this even further. So SMART, as Shahzad mentioned, is the software system used by conservation areas around the world, not just for poaching, but for also other legal activities such as illegal logging or illegal fishing. And our goal is to expand beyond just those parks in Uganda and Cambodia and democratize AI and make this system available to park managers everywhere without having to go through the whole laborious process of back and forth iteration and month-to-month calls. So specifically, at this moment, we are in the process of conducting alpha tests in about 20 different national parks. So those include Cross River National Park in Uganda, Crown Bassa National Park in Liberia, and Kafue National Park in Zimbabwe. Slow process of deployment really started back, as Bishra mentioned, when we visited Srepok Wildlife Sanctuary in Cambodia, where we got to accompany them on a patrol and try to understand what their constraints were and how to actually use these AI predictions in helping to plan their patrols, and also chatting with them about how they go about their day-to-day and week-to-week and month-to-month operations, what different things they're looking at when they're trying to analyze the terrain, and also just understand how they navigate all sorts of on-the-ground challenges as well, such as if they see a footprint on the ground or if they hear something in the distance. Those all are things that they're considering as well. But the challenge is that these poachers are extremely successful. So here's just a sampling of sort of the arsenal of snares and other goods that these rangers have been able to remove from Srepok Wildlife Sanctuary. But unfortunately, wire snares are so cheap to make and so easy to deploy that poachers can just sort of blanket the ground with snares. So the estimate in Srepok is that for every 1 deer, there are 4 snares. So it's a huge challenge. And conservation biologists have estimated that rangers are only effective at removing about 10% of all snares in these parks. So even though they are making a huge impact and we want to remove as many as possible, hopefully we're able to do more than just prevent 10% of the damage. And specifically, the belief in conservation biology is that one of the most effective mechanisms for preventing poaching and other conservation crimes are through deterrence. So when rangers conduct patrols in certain areas, they dissuade poachers from coming back. But the question of how exactly are poachers responding to our ranger patrols and what exactly are they doing on a month-to-month basis or week-to-week basis has always sort of been an open question, both in computer science and in the conservation biology literature. So with the data that we had in these parks, we were able to analyze the relationship between ranger patrols and poacher activity, and specifically to we were able to extract this effect that we were hoping for, which is that there is deterrence. Ranger patrols are effective at deterring poachers from coming back to an area, specifically if a ranger spends more time, a few extra hours patrolling one target. In the next month, poachers are slightly less likely to come back to that area. But it's not quite so simple. So there's actually a displacement effect as well. So if we patrol one area more heavily, then poachers will actually move out to those neighboring areas. So they'll understand and react to our strategy. But this understanding of poacher behavior motivates new problems in computer science. So this gives us motivation to start exploring sequential decision making and trying to think, how can we plan patrols not just for the next month, but rather for the next 6 months, with the understanding that our behavior in month 1 will impact what the poachers are doing in month 5. And additionally, as we've talked through these alpha tests with our smart partners around the world, we've uncovered other challenges that they're facing as well. So in Uganda and Cambodia, we've had just, as Mila mentioned, we had 10 years of patrol data and just thousands of patrol observations over time. And many parks like that, such as Kruger National Park in South Africa, are very well resourced. They have drones, they have teams of rangers that are really able to cover the park comprehensively. But there are other parks, such as Bajo Madidi Protected Area in Bolivia, which was only established in 2019. This park, unfortunately, has just started the ranger patrols. They don't really have a good sense of what's going on, but it's completely succumbed to illegal logging. And this is also in a very biodiverse, rich area in the Amazon as well. So the challenge is, how can we take something that was successful in a park like Kruger National Park and make it successful as well in these new areas in Bolivia that don't have as many resources, that don't have as much data. And this motivates new computer science challenges as well to try to think, how can we fill in the gap? And there's 2 approaches that we've taken so far. The first is to think, what if there's not enough information about the geography of the land? So if we don't really know what the animal density is, or exactly where the water holes are and where the rivers are. So if we don't have GIS experts who can spend time and expertise computing all that information, are there other things that we can leverage? And what we found is that by using publicly available satellite imagery, we're able to recreate some of those features and produce estimates that are almost as good as the ones from these expert-created features. Additionally, for the challenge of what if there's not enough patrol information to really learn what that poacher's behavior is, this motivates a new algorithmic challenge in computer science in a subfield of machine learning called online learning, where we're not only trying to predict where the poaching hotspots are, but also to explore previously unseen areas that might be hotspots for poaching, and try to balance that trade-off, because we don't want to only spend time exploring, because that means we'll neglect certain areas that do have a lot of poaching activity, and then in that time, all those animals will be killed. So we want to make sure that we're sort of balancing going to new areas where poachers might be attacking with also what they're doing. And this poses a lot of interesting new work in computer science as well. So with that, I'll open it back up to Erwin. Thank you all so much.
So Lily, thank you so much to all of our panelists. Thank you for that great overview. What an amazing project, and what really an amazing team that we have in front of us and as part of this panel today. I think your collective vision and passion and dedication for this work and the accomplishments that you have to show for it really shines through. And I think if we were in person, we'd certainly try to give you a round of applause at this point in the discussion. Having said that, we have a bit of time, and so I wanted to dive in a little bit more deeply into some of the themes that you folks touched on. I'm going to start with, I think, a very fundamental but important question. I kind of want to know what drew each of you to, engage with this project. What piqued your interest about this particular activity, and how you felt as you went about it. So, Lily, I'm going to actually start with you, if that's okay.
So my motivation for working on a project like PAWS really goes back to my childhood, when I was just a huge lover of animals. And at 9 years old, I decided to become vegetarian just because I didn't want to think about hurting any animals in the process of my everyday life. So as I grew older and I started studying more math and computer science, I really realized that, okay, this is something I love a lot, but I'm not excited about it if I'm just thinking about things in the abstract. I really want some concrete problem to focus on. And when I was in college, I actually came across the field of computational sustainability, of which Bishra is one of the leaders, that's actually applying these challenges in computer science to problems in sustainability and ecology. And this really, really just excited me and made me realize that we can be mathematicians and scientists while also working on these other very, very important socially relevant areas as well. And through that, I came across Millen's work and I learned about the PAWS project and just knew this is how I really would be excited about spending several years working on.
That's awesome. Bistra, same question to you.
Yeah, so computational sustainability has really become kind of the driving force behind everything that I do. I believe that computer scientists and AI researchers have a big role to play in helping meet the greatest challenge of our century, which is achieving our sustainable development goals. And there's so much to do. There's so many amazing opportunities, and so many of them have not been taken up by AI researchers and computer scientists in general. And in my work early on in this context has been focused on actually leveraging AI for biodiversity conservation. I've worked a lot on using AI for spatial planning for wildlife corridors, for predicting species distribution under different climate conditions. And so when I joined USC and I learned about PAWS, that was just an amazing way of synergizing those efforts, and already kind of my built expertise into ecology together with now using AI for actually fighting poaching. And so for me, this was like a very natural synergy and next step, and it has been a very, very rewarding experience.
That's great. Shahzad, how about you?
Yes, for me also, I have always been very passionate about doing multidisciplinary research, like working with conservation biologists or environmental scientists was really exciting to me. And also I felt that in this project, there's a lot of opportunity to make an impact. So we were able to develop some tools that can help save wildlife. Some of these like wildlife species that they are endangered, they are iconic species, they are helping the biodiversity of the planet. So we could do something about it to reverse the downward trend in their population through this project. And additionally, like the park rangers that they are combating these armed wildlife poachers, they have a really difficult job. Every day they have to go to remote areas. They have to spend a lot of time with like limited access to facilities. So I felt that if we develop some tools, we can make a difference for the park rangers and conservation area managers. So this was really an interesting area of work to me.
That's great. Millen, how about you?
So my research has focused on AI for social impact in areas like public safety, public health, conservation being a newer area in that way for many years, 15 years or more. And the trigger for this particular PAWS project was a panel that was held at the World Bank 2010, 2011, when they had a global tiger initiative where only 3,000 tigers were left at that point in the world. And they were being, the basic slaughter of tigers meant that tigers would just be eliminated. And on this panel, I was invited as an AI expert to talk about how we could do something with AI. But all the other experts who were wildlife conservation experts were talking about, one by one, elephants, rhinos, tigers would all be just decimated. And so we would be left with a planet without all this magnificent wildlife. And so that just meant that it just seemed like AI could do something for conserving wildlife. It was a tremendous opportunity in terms of actually applying AI for something important to society. And simultaneously, there were such important research challenges as we discussed in terms of user-inspired research. So this is a challenge where I invite other scientists who are interested in this area to join the fight. We want to make sure that biodiversity is preserved. The scientists who are on this panel, my co-panelists, are very much dedicated to this cause, but we need more people to join this effort. And so hopefully they will join it after this panel.
Yeah, absolutely. You all talked about multidisciplinary research. I think this is almost opening up a whole new field when we talk about computational sustainability. You talked, Millen, about encouraging more folks to get into this field. I'm curious, maybe I'll direct this question to Shahzad. How are we thinking about education and workforce development in this particular sphere? What sorts of efforts has this particular project really surfaced in that regard?
So for me, I always wanted to do mathematical modeling, and I like when I was a PhD student and I started working on this project that was funded by NSF. I was able to develop the right skills, and also I was able to like build the confidence needed to start a professional career in the area of AI for good and AI for social impact. I think the process of talking to the domain experts and to the stakeholders was a really great experience for me. I was able to hear their concerns. I was able to hear their feedback and incorporate them into my mathematical modeling approaches. And I was able to design tools and models that were somehow designed to address their problems in their domain. So it really helped me to build the confidence and build the foundation needed to start my profession in industry. And I have been working along the same lines at Microsoft in AI for Good research lab in the last 1.5 years after I graduated from school.
Got it. Milind, we're running out of time, actually. We could talk for hours, I'm sure, about this topic, but I want to give you maybe the last word. I'm curious your take. This project has largely been supported by NSF over the years. I'm curious, what would you say has been the most significant impact of this federal investment here?
So these projects for AI for social impact, whether it's for wildlife conservation, for public health, for youth experiencing homelessness, or other kinds of projects that are really focused on the marginalized communities, on the endangered communities. These are projects that are not of commercial benefit, nor are they sort of national defense priorities, but these are important for society. This is AI for the humanity that has not benefited from AI, the 99% who are really in need of ensuring that we develop the benefits or deliver the benefits of AI to them. And what National Science Foundation and funding has done is really allowed us to focus our effort in terms of this use-inspired research to deliver these benefits of AI while simultaneously generating newer research challenges for AI. And so we are grateful for the support of the National Science Foundation to support causes for efforts in AI for social impact. And we hope that these kinds of efforts will continue and that there will be continued support for AI for social impact that would not only benefit science, but at the same time deliver results for the marginalized, for the endangered communities. So thank you very much. And thank you to all the co-panelists for all the great effort that they have put in to PAWS and for AI for social impact in general.
I think that's very well said, Milind. And I'll just say, you thank NSF, you thank your co-panelists. I'm just going to thank all of you, right? Not just for taking part in this panel today and really articulating the value proposition of use-inspired research and the prospect of AI innovation when it comes to having societal impact in areas like conservation and sustainability. But really, I thank you for your vision and your leadership and your commitment, because it's researchers like you, it's folks like you who have the ideas and who have the willpower to take on those ideas and really pursue them that ultimately leads to the kind of consequential impact that we all live with. So, in a very positive societal good kind of way. So Milind, Shahrzad, Bistra, Lily, thank you all very much for joining us as part of this South by panel. Thank you all for very much taking time out of your busy schedules to be a part of this and hear this discussion. And we certainly look forward to seeing where this project will go in the years ahead. Thank you.